In this video, we're going to continue our work with probability tables, and what we're going to look at is how to determine if two events are independent. So two events are considered independent if the outcome of one event does not affect the outcome of the other. So there's two different ways that we can test for independence. So there's two different formulas. There's a multiplication rule and then there's the conditional rule. So multiplication rule, we'll think about what multiplication means. So it's the and. So basically, if the probability of A times the probability of B, so typically we say, oh, this is the and, but that is only going to equal the and if when you multiply the two individual probabilities, it's the same thing as the intersection. So remember we saw in the previous video with the probability tables, we saw the intersection, so the A intersection with B, we saw that that's the intersection of the row and the column. So if that ends up equaling the product of the probability of just A times the probability of just B, well then we know that the two events A and B are independent. So basically, if we end up with these rules being equal, so if equal, this implies independent. Not equal implies not independent. And one important thing to point out here is that we actually say not independent. We won't use the term dependent. You don't want to throw in another term. So it's going to be either you say they're independent or they're not independent, depending on if your rules end up being equal. So that's multiplication rule. The other option is the conditional rule. This is, remember, conditional means that there's a given. So the conditional rule is basically saying the probability of A is equal to the probability of A given B. So this would justify that events A and B are independent if these two probabilities are equal. So basically the probability of A is saying the probability of A out of everything is the same thing as the probability of A given that event B happened. This is also the same thing as saying the probability of event B is equal to the probability of B given A. So notice for these rules, the B comes first and then the A comes first for the other rule. So it's basically saying the probability of B out of everything is equal to the probability of B given that A happened. So those are your two options. So let's actually go through and try some examples so you can see exactly what you need to show for these and exactly what to do. So we start off with this chart. So it's talking about a simple random sample of adults living in a suburb of a large city was selected. The age and annual income of each adult in the sample were recorded. The resulting data are summarized in the table below. So we have age, and we're comparing that to annual income. So we have, looks like 207 total people, right? Because we can see that total of the column and of the rows. So we see what is the probability that a person chosen at random from those in the sample, so out of everyone, will be in the 31 to 45 age category. So out of everyone, so out of 207 people, how many are in the 31? So 31 to 45, go to the end of the row, 89. And again, we'll just leave that as a fraction. What is the probability that a person chosen at random from those in the sample, so again, from out of everyone whose income are over 50,000, so actually let me reread this, it says, what is the probability that a person chosen at random from those in the sample whose incomes are over 50,000? So that's actually a given. So given that the person's incomes are over 50,000, what will be the probability that they will be in the 31 to 45 age category? So out of those who make over 50,000, so out of the 96 people in this category, what's the probability that they're 31 to 45? So it'll be 35 out of the 96. So see the differences between A and B? This says chosen at random from this sample, so meaning out of everyone, versus this one says chosen at random from the sample whose incomes are over 50,000. So that's kind of like a hidden given because it doesn't just straight out say given this or if this, but it tells you who you're selecting from. So just be careful when you're reading these. So then for part C, it wants us to know from A and B, so using our results from A and B, is annual income, so is the income independent of age category? So here's what's important. When you're trying to test if two different categories are independent of each other, you can pick any probabilities. So meaning I can pick any specific category that I want to compare. So I can pick any age category and compare it with any income category and use one of these two formulas to test it. Since this problem says to use parts A and B, that means I'm going to use these two results. So meaning I'm going to use the category of 31 to 45 with the over 50,000 because that's just what was given to me in the previous parts. If it didn't tell me that, I would pick anything. So what I'm going to do is I'm going to go ahead and I'm going to show you both options for your test. So the test for independence is what this is called. And there's going to be two options. So option number one, let's use the conditional rule. It doesn't matter. I'm just going to pick the conditional rule. So what that means is I want to test is the probability. So what I have in part A is a probability of someone being 31 to 45. So I want to know, is that equal to the probability of being 31 to 45 given that your income is over 50,000? So that's the conditional rule. I'm basically taking and I'm plugging in these different scenarios here. So I know the 31 to 45, that probability is 89 over 207. And this probability was from part B is 35 over 96. This is where now I really want to convert these into decimals. I don't want to try to compare these fractions. So what we want to do is we want to get decimals. You want to get as many decimal places as possible. So when I converted this to a decimal, I got 0.429952. And I convert the other, I get 0.364583. I see that those are not equal, which tells me that these events are not independent because I get not equal. So before I write my conclusion here, I'm going to show you the multiplication rule and then we'll just use the same conclusion for both because it's if you use conditional rule and you get not independent, well then when you do the multiplication rule, you also have to get not independent. So let me go ahead and do the second rule and then we'll write our conclusion. So option number 2 is to use the multiplication rule. So this would mean the probability of over 50,000 times the probability of 31 to 45 would have to be equal to the intersection of those. So over 50,000 with the 31 to 45. So what that means is I would go and I'd look in my table here. So over 50,000, we don't have that probability already given to us. So over 50,000 is going to be 96 over 207. The probability of being 31 to 45, we have that over here, so that's 89 over 207. And then the probability of being over 50,000 and 31 to 45. So over 50,000, so this column with 31 to 45, that's going to be 35 out of the 207. And again, I should have question marks here because I don't know if these are equal. I'm trying to see if they're equal. So now I'm going to go ahead and I am going to multiply these. So 96 over 207 times 89 over 207. So this gives me 0.199397 with some more decimals. And then 35 divided by 207 is 0.1690821 with some more decimals. I see that, again, they're not equal, which is what we expected because we already found out in the first one that the events are not independent, so we should have gotten something that was not equal. And just remember, I don't have to pick these two categories to compare. I could have picked over 50,000 with 46 to 60 as my age range, and then I could have used the same thing. I would get different decimals in the end, but you would see that the two decimals on either side of your formula wouldn't be equal, which tells you not independent. So basically your work for this, you have to show one of these things. You have to write, okay, this is my rule, my formula that I'm using, and you plug in. And then the last thing you have to do is you have to write a conclusion. So my last step here is my conclusion. So I would say age, so the two categories we compared were age and income. So age and income are not independent. Again, make sure you say not independent. You don't change this to dependent. So not independent events because the probabilities or their probabilities. So basically the formulas when I'm saying their probabilities are not equal. And that's it. So that's the process. So it's the same process every time, but let's go ahead and let's just try a couple more so you can see. So let's go to the next page here. So now we're comparing math classes, the enrollment of math classes. So if we look, what is the probability that a student will take calculus? So out of all these students here, what's the probability that they take calculus? So there's 90 students that take calculus out of the total. So 90 out of 675. And then it says, what is the probability that a 12th grader will take calculus? So now we're saying that if you're talking about a 12th grader, so given that they're a 12th grader, what's the probability that they'll take calculus? So out of all of the 12th graders, so there's 220 12th graders, what's the probability that they take calculus? So 62. Part C, what is the probability that a student taking Algebra 2, so for the students, so out of the students that are taking Algebra 2, so this is my given, what's the probability that they are a 10th grader? So out of the students taking Algebra 2, there's 213 taking Algebra 2. What's the probability that they're also a 10th grader? So 74. So now the next question is, are grade level and course enrollment considered independent events? So here's my two categories or events that I'm comparing. Remember, you can pick um, any condition or any category within those to compare. So whatever you want to pick. So You just have to pick any one of each category. So we have to pick a grade level and we have to pick a course that we want to compare. So if I pick 12th grade and calculus, since we already have some stuff up there, let's do that. So let's go ahead and I'm going to use the conditional rule because if I look at what I already found, not that it's very difficult to find it if you haven't found it already, but when I look at this, I know the probability of calculus and I know the conditional probability of calculus given 12th grader. So what I'm going to use is I'm going to use the conditional rule. And again, you might want to make a note to yourself. You can pick any category. It does not have to be calculus and 12th grade. It can be anything. You can use the multiplication rule every time if you would like. You can always use conditional rule if you'd like. You just have to pick something and you have to be able to get those probabilities from the table or from previous parts of the question. So for the conditional rule, I'm going to look at the probability of calculus. Is that equal to the probability of calculus given 12th grader? Because I already have those. So the probability of calculus is part A. So 90 out of 675. Is that equal to the probability of calculus given 12th grader? So that's 62 out of 220. And again, make sure whatever you pick for right here for this probability or this event, make sure that that comes first over here. So it should always be probability of calc, is it equal to the probability of calc given some other condition? So now when I look, I just get my decimals here. So for 90 over 675, I'm getting 0.1333. Is that equal to 62 divided by 220? I get 0.2818. So no, not equal. It will happen sometimes that they are equal, just so you know. But in this situation, because of this conditional rule, I just verified that these events are not independent. So now I can answer the question, I can write my conclusion, and I can say grade level and course enrollment are not independent events because their probabilities are not equal. So there you have a full like test for independence is basically. So you show your rule, you plug into it, you show that the decimals are not equal, or you show that they are equal, and then you write your conclusion. So then the last example here is a little bit different because now they're giving us probabilities as percents. So a lot of times we've been talking about probabilities as fractions, but keep in mind, probabilities can be percent. What's the percent chance that something is going to happen? It can be written as a fraction. You can also write it as a decimal. So there's 3 different ways that you can represent a probability. So whenever I get a question like this that has a lot of wording and some numbers in there, I like to kind of just break down what do they give me. So it says the school records indicated that 12% of the students at Pittsford Sutherland High School take AP Stats. So that tells me that, because it's out of all students, the probability of a student taking stats is 12% or 0.12 if I write it as a decimal. Then it says that 10% of all students take calculus. So the probability of calculus is going to be 10% or 0.10. And then it says if it is given that a student is taking calculus, so if it is given that a student is taking calculus, then the probability that they are also taking stat is 20%. So basically this is saying the probability of stat given they're taking calculus, this is the 20% or 0.20. So that's all of the wording right there is the same thing as me just writing it like this. So that's why I always like to kind of dissect the problem and write out all of the numbers. What are the numbers that they're giving us? So now let's look at what it says. It says state the complement of a student taking AP Stats. So complement is an important word. It means the opposite, basically. So probabilities can only equal 1 or 100%, right? That's the maximum you can have is you can be 100%. There's a 100% chance that something's going to happen. Or you can say 1 if you convert it 100% over to a decimal. So when we say complement, if I say, what is the complement of taking stats? Well, let's go up to our probability of stats. There's 12% of people that are taking stats or the probability of a student taking stats is 12%. So what's the percentage of the student not taking stats or the complement? Well, that would be 100% minus 12, so 88%. That's the complement. So let's just write all of that down what I just said. So this is basically saying not taking stats. So if the probability of stats is 12%, well, the complement, so the complement is written like this with like a little mark here, kind of looks like a little prime symbol. So this would be 100% minus the probability of them taking stats. So 88%. So that would be one answer. Or you could do this as decimals. So you could say, well, the probability of stats is 0.12. So then the complement would be 1 minus 0.12, so 0.88. So same answer, doesn't matter which way you give it, they're equivalent. And then it says, would you consider the events AP Stat and AP Calc to be independent? So for this, if I have to be a little bit more careful about what I choose, which formula I use, the conditional versus multiplication, because I don't have a chart with all of the information where I can just pick anything and compare it. I have to use what's given to me. So I only have these probabilities given to me. So that means I have a conditional. So that tells me use the conditional rule. So if I use the conditional rule, since I have a conditional probability, well, the conditional rule, so I have the probability of stat given calc. I want to know, is that equal to, remember what I said, whatever's first here has to match with what you're finding the probability of by itself. So the probability of, it would have to be the stat that I'd have to compare. So really this probability of calculus, you're not even using that. But it gave it to you, so you just have to be careful. So now I have, this is 0.2. Is that equal to 0.12? They're already in decimal form. So in this situation, compare your decimals, not the same. So therefore I can say the events I could say AP Stat, I guess I'll just write it exactly how they have it here. AP Calc are not independent because their probabilities are not equal. So again, same sentence at the end every time. If you got that the probabilities were equal, then the only difference is you would say the events are independent because the probabilities are equal. If they're not equal, then not independent. And it's basically the same sentence at the end. So that's it for using our tables for testing for independence. So go ahead and try the homework problems.